Okay, now that we've done the calibration for the synchronization, what I would like to show you is what we'll see when we use an arrow pulse. This is 4-sample pulse, basically every 1024 samples. And so I have this loaded into both AWGs. And since we've done the calibration already with the AWG, you could actually do the calibration with this pulse if you wanted to, no problem. So in order to show the synchronization, what I'm going to do is go ahead and arm the AWGs as we did before. Now, one thing I want to mention is that in order to get it to synchronize the first time, I mentioned that you would basically start it off by ascending the trigger and everything, and then you align the phase of each AWG. I have found that it does require that you actually stop the clock such that you're basically starting from scratch. Once you've stopped the clock, and the easiest method for stopping the clock is to go into your trigger menu. So if I go under setup and then trigger, under the clock menu, is we would just go to internal and then back to reference, and this will basically start the clock over again. So in this particular case, we're trying to follow somewhat of what was requested from a customer, and so anyway, now that we've got it all synchronized, we arm the AWGs, we go ahead and fire the trigger, and you can see that we're still synchronized in this case, fairly close. In a minute, I'll also show you the jitter profile on the sampling scope so you can get a little bit cleaner picture of what the actual trigger jitter is. This one I just want to show you quickly how well it synchronizes with each either. I could turn off the channels, so I'm going to go ahead and turn off the channels on the second AWG and then turn them back on again. You can see that we're still synchronized. I can do this several times, no problem. And I can do this on either AWG. Notice they stay synchronized. I could stop playing. If I stop playing the signal, what would require then is that I would have to stop the trigger and then go back and rearm each one of these and then start the trigger again, and still we're synchronized in this case. So again, the next step would be to show you exactly what the jitter profile is. We want to take out of the measurement the jitter of the actual oscilloscope, and to do that we really need a sampling scope in order to show the minimum jitter that we're getting. And again, the signal that I'm using right now is basically just a 4-sample pulse, which correlates to the signal that you required. And basically I made the waveform long enough that it fulfills the 2400 point requirement for the 2-channel box. We're still synchronized, and now I am showing the 8K sampling scope with a phase reference so that we can see the actual jitter. And you can see in this case we're looking at, it's probably pretty hard to see on the video, but we're looking at about 270 femtoseconds of jitter on each of these channels. Now what I'll do is I'll go ahead and turn the channels off again. on the AWGs. So this is all 4 channels from the AWG, from 2 AWGs. Now that we have everything synchronized, you can see that no matter how often we turn off the channels and turning them back on again, we stay synchronized. And again, basically the phase reference capability of the sampling scope is going to give us the best of all performance, but still you're going to be limited to the phase characteristics of the reference clock. And so you could get even better performance than this if you used a better reference clock than what we're using with the AFG. But I think in the long run, we're seeing, like I said, around 300 femtoseconds, and with a better reference clock, we can probably get that down to 100 femtoseconds of actual trigger jitter. And again, every time you turn off the waveform and then back on again, we can see that we're staying synchronized. The other thing I want to bring up, the only time that, or the time that you'll have to do recalibration of the synchronization is if you stop the clock on either one of the AWGs. And in that case, you can change waveforms, no problem, and stay synchronized. You can turn the channels off and on and stay synchronized. But if you change the sample rate, then you're going to lose your synchronization, and you will have to recalibrate again. So I assume that in most cases you want to be able to turn the channel on and off again and make sure that they're synchronized. And I can do this 10 times just to show you that we do not lose synchronization. And the drift, if there's any drift at all from this characteristic, will mostly be temperature drift. So if you're in a fairly contained room, you should not see much drift at all. We're probably talking a delay drift of, again, in the femtoseconds. So we will easily be able to meet a lot of applications that are requiring at least 5 picoseconds of synchronization. We can do well below 1 picosecond of synchronization. So anyway, this is a good example. So hopefully these 2 videos that I built today will clarify that we are able to synchronize very well and have the capability of changing waveforms, turning the channels off and on again.